welcome to the module. Now, we will be discussing about implementation of a temperature controller using LabVIEW. In last modules, we have seen the use of LabVIEW data acquisition device, and we have also seen about a virtual bench that we have in our clean room facility. So, to just make you understand about how to make use of a data acquisition unit using LabVIEW as well as a CDAQ, I just developed a case study. So, before going into the case study, I would like to make you understand about how exactly this works and what exactly that I am going to do in this case study. So, the idea of this case study is that I have a plant which was equipped with a temperature sensor. By using software, that is by using a LabVIEW and by using a data acquisition unit, we will be controlling the temperature on the plant to be as our required set point. So, in order to understand what do you mean by set point, how exactly it works, we should understand about a closed loop control system. So, to give you a brief understanding about what is a closed loop control system, how does it look like, this is if you look into the screen, here we can understand how a closed loop control system looks like, what do you mean by negative feedback, everything. So, how exactly it works in the sense, here you will have an error detector which is nothing but which finds the difference between the system input and your actual input, actual output. That means that if I say the temperature on the plant to be of 50 degrees centigrade, the error detector finds out what is the required temperature, meaning 50 degrees, and what is the current temperature on your plant. So, if the plant temperature is below the required temperature value, obviously the error detector will gives you a positive input voltage, right. So, by passing through different controllers, right, different controllers in the sense either P controller, PA controller, PID controller or on off controller, by passing through the on off controller, based upon the quantity of an error, it will generate a manipulated variable. This manipulated variable is responsible to provide power to the heating circuit such that it heats to the required set point. So, as a result, because of that reason, it starts heating, and as long as the system output, as long as it is heating it, the system output will start increasing, meaning the temperature will start increasing. So, when the temperature starts increasing, the error value starts decreasing it. So, this is a general way of understanding about a closed loop system and the representation of a block diagram of a closed loop control system. But in this case, what I am going to do is that, as we have already seen in a hardware part, how do we realize a P controller, on off controller, PID controller, everything using operational amplifier. But in this case, what I am going to do is that this complete controller we will be developing using software, meaning in this case we are going to use LabVIEW, which is nothing but laboratory virtual instrument engineering workbench. So, using this software we will be developing the required controller logic, which is nothing but a P controller, PA controller, PID controller. Even in case if you want, you can also go with different other compensator circuits too inside the controller. And since it is in a software, we have to provide a system which converts a real world signal into digital, because since the controller is realizing in a software will understand only digital data, but as well as the real world signals are completely analog, we should also have to have a converter unit which converts your real world signals into digital signals. As a result, what we are going to do is that we will be using a data acquisition device. So, the data acquisition device that I am going to use here is a compact DAC, which we have already seen in our previous sessions. Now, I am going to show how do we connect the same circuitry what we have discussed using data acquisition device, right, and I will also give you the brief understanding about the data acquisition device and the chassis as well as the signal conditioning modules that we have and to where we are connecting it, and as a part of it I will also make you to understand about what logic that I am going to develop in LabVIEW, how exactly it is going to work. Also, in order to set the gains of a controller, one thing we should also have to understand is that the plant circuit. As we have already seen about the plant circuit, again I would like to make you understand about how exactly it works, and depends upon the plant circuit, the manipulated variable, the range of the manipulated variable and will be completely set. And the manipulated variable is nothing but an output of a controller that entirely depends upon the tuning parameters that you are going to set on your PPI PID controllers. So, as a result, the understanding of a heating circuit is must. And whereas when I say temperature, it is not sensible in terms of, or since it is a temperature and since we are interfacing to an electronic unit, it is very hard to realize there is a change in the temperature by looking. So, we require to have some sense by either by using touching or by using some kind of a sensor which converts this temperature change into electrical output voltage. Since we are completely realizing using an electronic unit, we also require an sensor. So, we will be using an LM35 sensor which will be stick on top of a plant, so which senses the temperature. And since the sensitivity factor of the system input, the meaning that since it is an electronic unit, the input that we are going to set should also be in form of voltages. So, that means we should know what is the sensitivity factor the sensitivity factor of your system input. Meaning, if I say if I apply 5 volts, what it means that how much temperature that it should be there on top of a plant. So, in this case I am considering 0.1 volt per degree centigrade. That means, if I give 1 volt, it means that it has to maintain a 10 degree on top of a temperature. If I give 10 volts, it should maintain 100 degree centigrade. That is nothing but the sensitivity factor in this case. And whereas the signal conditioning circuit is important in case of a sensor, because whatever the output quantity that it is going to provide by a sensor may not be exactly matched with respect to a system input. As a result, you have to convert the output of a sensor data into the system input quantity or a scaling factor. So, in this case I am going to use a scaling factor of 100 such that both the system input factor as well as the output factor will match, right. So, let me briefly explain you about the working of the plant unit. So, we will be using an operational amplifier. The purpose of an I'll make you understand about the purpose of an operational amplifier too, and we will be using a Darlington pair transistor. The purpose of going with the Darlington pair transistor is that since we will be working on heating of a plant, the temperature entirely depends upon the power that we are going to supply in this place. As a result, we will be working with higher currents. The power is of really higher, the current is also really higher. So, that is the reason your transistor should be capable of withstanding such a higher currents. As a result, we require to go with a Darlington pair. So, 2N3055 is an inbuilt Darlington pair which has a Darlington pair configuration inside, so that it can withstand up to a current of 10 amps of current. Now, if you recall, as we already know the working of an operational amplifier, so how does exactly it works in the sense, this is the input to the plant which is nothing but the manipulated variable which we are getting from the controller will be connected to the positive terminal. Let us take, we have a manipulated variable of 0.5 volts. Since the positive terminal is connected with the 0.5 volts, the negative terminal will also be at a 0.5 volts. As a result, the voltage drop across this R1 resistor will be also as 0.5. And since this is a transistor, if you recall your transistor working, right, the current flowing through the collector is almost equal to the current flowing through the emitter, and the relation between the both things is a proportional, and the proportionality constant is called alpha, right, and which will be almost equal to 0.99. So, as a result, I can say the current flowing through IC as well as IE, we can almost make it as equal. So, if you know the current flowing through this emitter leg, we can easily understand the current flowing through the collector. Now, in this case, since we are applying 0.5, the voltage drop across this R1 resistor will also be a 0.5, and since we know the resistance value, and since we are forcing the voltage drop across the resistor is also a fixed value, we can find out the current flowing through this emitter leg, right. So, if I want to calculate, so 0.5 divided by 0.1, which is nothing but 5 amps of current will be flowing through this emitter leg when we are applying input of 0.5 volts, right. So, because of the forcing, because of the negative feedback connected to an operational amplifier, it forces the voltage drop or it forces the current flow through the transistor to be of 5 amps in this configuration, right. So, whenever we change the voltage across the positive terminal, as a result the voltage drop across this resistor will also changes, right. Since the resistor is fixed, the current flowing through this also changes. That is why this is also called a voltage controlled current source. By changing the voltage, controlling the voltage at the input, we can also control the current flowing through the circuit. So, that is why this is also called voltage controlled current source. But you may ask, you may not understand how exactly it is going to generate an temperature on top of a transistor, right. So, in this case what I am doing is that I am generating temperature on top of a transistor. How? So, if you understand, if I do not have this negative feedback, if you see it is not in a forced condition. So, whatever the voltage that you are applying, the complete voltage will be dropped across this particular resistance value, and the drop across this collector emitter will be 0.7 in a normal case where you do not have a negative feedback. But in this case you have a negative feedback. Because of this negative feedback, it forces the voltage drop across this resistor to be 0.5, and the input voltage applied is of 15 volts. As a result, what about the rest of 14.5 volts, right? Energy neither be created nor destroyed. As a result, the voltage drop, the remaining voltage will be dropped across collector and emitter junctions of a transistor. So, the amount of current flowing through and the voltage across collector and emitter both together, the power across the transistor at collector and emitter leg will be too higher, it causes the transistor to heat, right. So, higher the current, higher the voltage drop, higher the current flowing through, right, higher the power, higher the temperature generated on top of it. If you want to understand how much temperature is going to generate, if you look into the data sheet of 2N3055, you can understand about the relation between power and the temperature generated, right, from the data sheet. So, as a result, as this voltage is keep on increasing, the current flowing will be keep on increasing. Even though the voltage drop across this will be keep on decreasing, the overall the power will be multiple times. It will be a multiple. As a result, the power across this collector and emitter will be too higher, which will starts heating the transistor. So, this is how we have used the plant circuit using operational amplifier and the transistor as an heating unit. Now, since our idea was to control the temperature on top of the plant, what we are doing is we are using a controller. So, as I discussed previously, the controllers that we are going to see is of P or PI controller, and this is completely realized or completely developed using a LabVIEW software. So, this is also called as software in loop, meaning your controller will be a software which is in the loop, whereas the plant is an hardware which is an external, right. So, we are constructing the plant on the real world, on the outside, and the controller as in software. As a result, it looks like a simple software in loop configuration. In order to communicate between your software to your external world, you require to also have a data acquisition unit. So, even for acquiring the data into the system, even for generation of data from the system, we always require DAQ, data acquisition unit, which performs both acquisition as well as in generation too. I will show you how exactly that we are going to do using a LabVIEW. So, first, in order to make you understand, I would like to show the circuit that we are going to use in this case. So, if you look into the breadboard, that is a circuit that we are using. So, this is an op-amp 741 op-amp that we are using, and this is an 180 ohm resistor which we have seen in the circuit, and this is 5 watt 1 ohm resistor in this case, sorry 5 watt 0.1 ohm resistance, and this is connected as shown in the previous figure, whereas this is our 2N3055 transistor, right, and on top of it I have attached LM35, which is a temperature sensor. Now, by using this power source, I will be powering the complete circuit as well as powering the LM35 unit too. And whereas here you can see the data acquisition unit, this is called compact DAQ. So, this is connected through LAN, connected to the LAN, so that using LAN the data will be transferred between the PC as well as to this device. So it has a different signal conditioning modules. So this is different signal conditioning modules you can see here. So one for different applications, one to generate analog voltage, other one to acquire analog input data, to acquire the signals, analog voltage as well as current. Anything can be acquired using this particular chassis. This is this particular signal conditioning. This is NI 9207, whereas this one is NI 9263. By using these two modules, signal conditioning modules, whatever the data it is being generated from temperature sensor will be acquired, and as well as, since it will be compared with with the set value by using a differentiator, right, the error output signal will be sent to your controller. The controller, it generates a manipulated variable based upon the error signal that we have, and that the signal whatever we are generating will be generated using this 9263, and that will be given as an input to the positive terminal in the plant, right. So in order to understand that, let me show you how do I construct the system. Whatever the chassis that we are using is CDAQ 9189, and we will be using module 7 as well as module 8. Now to understand about module 7 and module 8, here we can see. So 9207 is the module whatever we are using, and if you see the first terminal AI0 plus and AI0 minus are side by side, right. The output from the temperature sensor will be connected at this point and at this point. This is ground and this is the output voltage. So that since it is connected to the acquisition pin, AI represents analog input channel 0, acquisition, it records the data and display in a software, right. And whereas for generation of a signal we will be using module 8, which is 9263. When you look into the device pinout, so it has a total of 4 channels, right. So AI0 common, AI01, AI02 and AI03. I will be using 6th and 7th pins, or 0 and 6 and 7 pins. So I will be using the 3rd channel, right. So these are I am going to use it. Now how do I construct a logic? So for that we require to go with we have to develop a logic using a software. So I am going to use LabVIEW. I will be opening a new VI. I am pressing Ctrl T, so that both the VIs will be accommodated side by side. Now this is called the front panel. So which is nothing but user understandable user understandable space, and this is the block diagram, which is nothing but your actual logic will sit. So when you are running the program, you do not have any access to your block diagram. So once the program is running, you cannot change anything which is available in the block diagram, but user has a space to change completely in the front panel. Now whenever I create some signals here, whenever I create some indicators or controls in a front panel, and automatically that corresponding you can see here a corresponding block will be created even in a block diagram. So that whenever we change or whenever it displays here, automatically it will update even in the front panel as well as a block diagram too. So now in this case our idea was to develop a temperature control. To make it more unique, what I will do is that I will take the inputs and outputs in the same fashion. So what I will do is that first as an input I will take it as a thermometer. So thermometer represents you what, like a temperature increasing and decreasing. So to make it realistic, okay. So I am changing it to control. So right now this is a control, and I will make it as digital display. So whatever you are setting it here, either you can set even by using the digital display, or even you can set using the hand tool too. So naming it as set point, set temperature, okay. So whatever the required temperature that we require, we will be setting at this point. We will be setting using this. Now, other one is we also require output temperature. So, but this should be indicator, right. So, this is an indicator. So, it tells you, it gives you the information of what is the actual temperature. That means it displays the temperature of the plant. That means the output of the temperature sensor is connected to this particular icon. So, when I look into the block diagram, here we can see that whichever we have created on the front panel, the appropriate icon has been even created in the block diagram. So, whenever I update here, automatically the value will be sent at this point. If you want to understand this, what I will do is that I will connect output of the set point to the actual temperature. Now, let me put highlight execution so that the executional speed will slow down to human understandable values, and we can also see what is the data passing through the wire. Now, let me run. I am making it as a continuous run. See, the set value is 34.29. Let me extend this. Here we can see the set value is 34.29. Since the output is directly connected to the set temperature output is connected to the actual temperature input, here we can see whatever I do in the set point, the same thing will be updated even here. It is a one-to-one connection, that is the reason, right. So, but we require the actual temperature value from the temperature sensor. Okay. So, let me show you how to do that, how to do the connections. So, if you look into the block diagram, now what I am doing is I am changing it to the icon level. So, this is the set temperature and this is the actual temperature. So, set temperature is nothing but what? Set temperature is from is nothing but user input, how much temperature that the plant should have. So, that will be completely set by using this. So, by using a software I am using in this case. Now, since it is a controller, we have a toolbox, we have a separate toolbox in our LabVIEW, that is called control and simulation toolbox. Let me keep control and simulation toolbox, and since I am doing the simulation, I will be using a control and simulation loop. Right. Now, so the input that should be passed through your controller should be an error input. So, how do we get an error input? One thing is, whichever the temperature that we set minus actual temperature. So, how do we understand actual temperature? In order to understand about an actual temperature, we should acquire the data by using data acquisition unit, right. So, if you want to create a block for acquiring the data from the external world, we have to use measurement and IO. So, in this case, what I will be using is that I will be using low level VIs, and I will be creating a channel, and it should be analog input because I have to acquire the voltage, that is why analog input voltage. Whereas, from which channel? So, I have to select from which channel that I have to do. So, let me make it as a control. Input channel, temperature, this is nothing but temperature input channel, and I will be placing it here. So, we require input channel from DAQ NI9207, which is nothing but, if you remember here, for acquisition we are using module 7, and if I look into the device pinouts, AI0 plus and AI0 minus, right. So, the module pin is module 7. So, I will be selecting CDAQ 9189 module 7, sorry, I have to go for module 7, yes, module 7 AI0, right. This particular pinout has a total of 8 input channels of analog input and a total of 16, right, 16 channels. So, in that I am selecting only AI0 channel. So, here we can see CDAQ 9189 module 7 AI0. So, since we have specified from which channel that I have to acquire the data, it passes through this particular block. This is nothing but virtual channel, DAQMX create channel. Then after that, I have to read the data. So, by using this block, whatever the data that is there in this channel will be read and converted into digital because of onboard signal conditioning unit which is available, the onboard data acquisition unit, which is nothing but your PGA or amplifier as well as an ADC. It has an onboard everything on that module. So, once it is converted into digital data, it will store in a buffer, and from the buffer I have to read the data. So, for reading it, I will be using a read block here, DAQMX read. Label. So, DAQMX read, right. So, since I have to read the data whichever get from this DAQMX create virtual channel, I have to connect the output of task to the input of the task of DAQMX read, and it is always a good practice to connect error block from the output to input. Now, if you want to understand what different configuration terminals that it has for this channel, press Ctrl H so that we can see the context help, and this is DAQMX create channel. If you look into this channel, few things there are different input terminals as well as an output terminals, and few things are displayed in terms of bold, whereas few things are normal text. The bold indicates it is compulsory, it is mandatory. Until unless you connect, this block cannot work, otherwise it throws an error if you do not connect it. Whereas the normal text indicates it is recommended, it is required, whereas others are recommended, right. So, if you connect it, it will consider those values. If you do not connect it, it will consider the default values. If you want to have much more information of this, if you go to the detailed help, press on the detailed help, the complete understanding of all the input terminals and the default values that it set can be completely seen here. Right, completely can be seen in the help. Right. Now even for in case of DAQMX, it is also same. So, tasks or channels in has to be connected here, error in has to be connected here, and this is optional or recommended. Now, whatever the data which is there in the buffer will be displayed at this point, right. So, this data is nothing but your actual temperature data. This is our actual temperature, right. So, the output from the LM35, if I connect it to module 7, which is nothing but NI9207 at analog AI0 plus and minus terminals, that value will be displayed here. Okay. So, to make it more short, what I will do is that I will create a sub VI. So, if I want to create, go to select those components, go to edit and create sub VI. Now, this is the sub VI which we have created. So, I will be editing it for our understanding. Okay. I am not going to write anything, but I am not going to do any documentation in this case, but it is always a good practice to do the documentation. So, I have to save the data. So, what I will do is that I will create a new folder in documents by saying temperature controller underscore SIL software in loop. Right here, I will be naming it as analog input AI channel info, AI channel. Okay. So, this I will make it as icon, this also I will make it as icon. Okay. Let me save. So, now the input channel I have done. So, whatever the data that is available will be displayed on this actual temperature. So, till here it is clear, but Okay. So, till now this is clear, but it displays. But what has to be done? So, once we get actual data into the software, it has to be compared with your actual value, and we have to understand the difference between your actual value to the set point. How do we do that? In order to do that, we have to use an error detector. So, for that I will be going to control and simulation, and simulation here. Here we can see different other pellets and the blocks. Here you can go with an summation tool, signal arithmetic. In a signal arithmetic, here you have summation and gain blocks as well multiplication. Right now I am going to use summation block. Okay. So, now I am naming it as an error detector. When I do an error detector, the first step is that the output of the set point has to be connected to the positive terminal. Now, if I directly connect it, the sensitivity factor of the set point, scaling factor what I mean, as well as the output of the LM35 scaling factor is not same. The reason is that the LM35 has a sensitivity factor of 10 millivolt per degree centigrade, but it has 0.1 volt per degree centigrade. So, you have to amplify the output of the signal to the required temperature value by using an amplification factor of 100. So, what I will be doing is, I am going to numeric. Here I will be taking a multiply. The actual temperature value will be multiplied with a factor of 100. So, that both right now, after multiplying it, both will have the same units. So, 10 millivolt into 100, which is nothing but 0.1 volt per degree centigrade, even this 0.1 degree centigrade, right. So, since it is easy to understand the signal which has the same unit, what I will be doing is the actual temperature I will be connecting it here. So, both are having in the same unit. So, easy to realize. Now, after doing this, we get the error signal. So, this has to be passed through your controller. So, depends upon what type of controller that you are using, that particular block has to be, logic has to be implemented. Either I can create the logic of a P controller or logic of integrator as well as differentiator, and I can do that, or LabVIEW already had, this particular software has onboard VIs where you can see it in control and the simulation, and in the simulation here if you go to continuous linear systems, here we can see integrator, derivator too. So, I can say I can take integrator, I can take an integrator, and I also require the gain blocks. So, here I will be going to control and simulation, and this is the simulation. So, let me keep this on. So, signal arithmetic, here you have gain. So, I am taking it as proportional or Kp, proportional gain, and I also require integral gain. So, let us take it as Ki. I also require derivative gain. So, let me take it as Kd, right. The summation of all these three, P plus I plus D, is nothing but your PID. If you make Kd as 0, it is nothing but P plus I. If I make Ki as well as Kd as 0, it is nothing but P. So, since we require 3, I will be using this and this as also positive. Now, I have all 3, I will be adding it up. This one, as well as this one too. Right. So, the output of this has to be connected here, one, and another one is integration with the gain, Ki gain. and another one is differential gain. So, I have to go with the continuous, and here you have a derivative, S represents derivative, connecting it here and the connecting it here. Clean up wire. Now, so the complete Kp, Ki, Kd gains are done, but since we have to change the gain settings, what I will do is that rather than making it a configuration dialog box, I will create a terminal, right. So, by using this terminal, here I can create a control. So, I will be selecting the control. So, what I will do is I will go to front panel, go to the numeric, I will create a slide, horizontal pointer slide. I will also create a visible items, digital display. This is for Kp, this is for Ki, this is for Kd. So, this I am naming it as Kp gain, this Ki gain, and this I am naming it as Kd gain. I may not be required this much of value. So, because when you observe the complete the voltage manipulated variable should be within the range of 0 to 1 volt. So, what I will do is that I will change the gains to be somewhere around max of 0.5, this also 0.1, this is also 0.1 something, later on I will change. Now, I have created those. Here you can see Kp gain, the block, appropriate block for that for whatever we have created in the front panel, that I will be connecting it here, and similarly for Ki gain from here I will be connecting it to. So, now I have to change it to terminal. Okay, changed from here to here. Even the same in case of here too, I have to change it to terminal, press OK. Then Kd gain, make it as icon, connect the output here to here. So, both Ki, Kp, Kd, PID controller is constructed in software. Now, what to do? Now, using the software we have done a controller. What is the next step? Whatever the data that is based upon the logic it is going to generate, that is nothing but here manipulated variable, right. That has to be given as an input to your plant. If I want to give it as an input to the plant, what I have to do? I have to send it to the real world or send it to the external world. But whatever we have designed in a PC, everything will be in a digital. How do we do that? Again, we have to make use of data acquisition. So, in a data acquisition unit, we have to generate, we have to use a generate signals. So, how do we do that? For that, what I will be doing is, I am going to measurement and instrument. So, here I will be using create channel 1, but previously we have used analog input read, now we will be using write, that is it. So, but now it should be analog output, not the input, should be the voltage, and single channel, single sample and DBL form. So, this should be connected here, this should be connected here. To make it understand, let me press Ctrl H. Here you can see the complete physical channels information, and here we can see autostat. If you require autostat, yes, create constant true. Okay, the data. This data is nothing but this value. But to which channel? So, in order to generate the channel, I will be going to I will be creating a control, renaming it as output channel. Output channel. Now, which channel? So, if you recall, if you look into the device pinout, we will be using NI9263, which is a module 8 in this case, and we will be using AO3 9189 module 8. Only one in this complete chassis, I have only one analog output module, say AO0. Right? So, I have selected it, done. Now, since it does not look like this, what I will do is that I will select everything, right, and visible, edit, go to edit and make it as create sub VI. So, sub VI is done. So, let me change everything. Now, the complete channel information, everything is provided. What are the signal that I am getting here? Okay, let me change the connection. So, output channel, this one. So, this particular terminal I am connecting it here. So, whatever the result I am getting, I just simply connected here. Now, everything is okay. Everything is so. Whatever the data that we are getting, everything will get it here. Now, it has to be even displayed, right? So, in order to display it, what I will be doing is, if you look into another actual temperature that we have seen, right? Okay. So, I will be creating one more display. So, in order to create a display, I have to go here. So, make it as numeric indicator, just to see what is the manipulated voltage value it is going to generate. So, I will say MV, which is a manipulated variable, and this I will be connecting it here. Okay. Okay. So, one thing is, this is the set temperature, this is performs difference between or calculates the error value, calculates the error, acquires the temperature data from temperature sensor, whatever I am doing is writing a comments, sensor and amplify, and this is nothing but controller logic. So, summation of controllers. To generate the output voltage. So, everything is okay now, but the major thing is that, okay, let me save this block too. So, I am naming it as main temperature temp main. So, even here let me rewrite. So, I will be taking it out completely. And this is my block. This is this. This is temp, and this one is main. Okay, this is done. So, but the analog input channels as well as analog output channels can it has a particular range above which and below which you cannot work. So the range of analog input is maximum is of plus or minus 10 volts, even for analog output is plus or minus 10 volts. So in order to not to have any complications since it is a simulation, so by observing into the logic that we have created, the output channel can also provide it with higher values too. So in order to not to damage our signal conditioning units, what I will be doing is I will be creating a stop execution thing, right. So I will be creating the stop execution and I will show you. Now if you see that this is our final circuit. So I have created even for if the input voltage is greater than 9, it will automatically stop the simulation, everything, and this is how the front panel looks like. Okay. Make current value default. Okay. So let me make it a set point as 50 right now, and the gains have also tuned previously, and those values I am using it here, right. Right now I am realizing only P gain and K gain. So to make you understand about the proportional gain as well as integral gain, what I will do is that first I will make even I gain as 0, only P gain is there, which is 0.02. I will be slowly increasing the value to. Okay. So this is our complete circuit. Now before running the circuit, let me do the connections. The output from the system should be connected to the input of data acquisition analog module, and output from the data acquisition has to be given as an input to the system. Output from the temperature sensor has to be connected as an input to module 7. So what I will be doing is that the temperature sensor output, this I will be connecting it to the first channel. So since it is a spring connection, press connect. So the output of this is connected, and the grounds also has to be connected here. I will be connecting it. So both the channels I have shorted, right, negative terminal to negative, and to the power supply. The output of the LM35 is connected as an input to this. So whatever the output, whatever the temperature sensor, the temperature will be displayed on at this point, actual temperature, with an amplification factor of 100. So since we are looking into in degree centigrade, if I multiply with 100, it gives me the actual temperature value, right. Sorry, in this case we are using a sensitivity factor as 1 per degree centigrade. So since it is a digital representation, I cannot even say whether it is a voltage or something. 1 per 1 degree. So if it is a 1 degree, it shows 1 degree. If it is 10 degree, it shows 10 degree. If it is 100 degree, it shows 100 degree. So that is why we are multiplying with a factor of 100 in this case. Okay. Now the temperature sensor, the transistor is connected to this, but output from module 8, which generates an output based upon the manipulated signal from the software, has to be connected as an input to this point at input 3, terminal 3. So for that, what I will be doing is I will be taking 2 wires. I am connecting it to the 6th pin. This is the input to the positive terminal, right, and I need a ground terminal. So what I will be doing is I will take one more black wire. So to the 7th pin I am connecting this ground, right, to here. Right. So let me switch on the circuit. Sensors requires 5 volts. Right now it is at room temperature. So let me run. When I run the circuit, right now the temperature is at 25 degree. The set temperature is 50 degree. Here we can see that the white one represents our set point, which is 50, whereas the red one represents your actual temperature, meaning the temperature on top of a transistor. So here we can see, so since there is a difference, right now it is at 47.9. So even though I will be keep on waiting, even if I increase the value to some 1 volt, right, we cannot see much change in this. So that's a problem with proportional controller when you are going with an higher order systems, right? When you go with an higher order systems, the proportional gain, even though if you keep on increasing, it will always have some offset. It depends. It depends upon what kind of system that we are using. So in this case, since we have applied a gain of 1, okay, so the temperature has increased. As a result, the manipulator variable is negative. Since it is a negative, the transistor will be in switch off condition. So by natural convention, it starts cooling. So let me cool down to 0 degree and we will show the response with 0.5. Generally, since we have increase in the middle of the state, it has worked in this way. So let it cool it down. So rather than stopping it, what I will do is that let me run it, but whereas I will be remove the power here. I will remove the power. Since there is no power, it will not heat anymore. Started cooling. Right now the temperature is at 49.4. So as long as, since it is a simple proportional controller, as the errors keep on increasing, the manipulated variable, since the gain is 0.5, the manipulated variable will also increase proportionally. Right. So let it cool down, and again let it cool down to room temperature. Again we will start heating with a gain of 0.5. We can understand that. Now the major problem with the gain of higher gains, because if you see the manipulated variable, whatever it is going to generate is a 5.6 volts. So now when you realize 6 volts applied as an input of the plant, it results in higher current, 6 amps of current. But you also have to see pumping 6 amps of current, whether your plant can withstand or not. If that is the case, you cannot go with a higher Kp gains too. That is another thing that you have to always remember, right? So even in this case, my power supply cannot provide more than 3 amps of current. So I cannot, one thing is I cannot go with 0.5 value. So let me change it to 0.2. So since because of the gain is 0.2, it is gone to 3 volts. 3 volts as an input to the plant. So maximum of 3 amps of current will be passing through that. So now it has reached to somewhere around 34.3 degrees centigrade. So let it cool down to some more temperature, some less value, even 3 amps. So let me take it to 0.3. Okay. It may be initially difficult to cool it down, but let me stop once again and run it. So it starts from 0 if I stop and run it. So before running it, okay, let me run it, and I am connecting the power here. Since I have connected a power to the breadboard, the temperature started increasing. 34. See how fast it started increasing. So the time it takes to reach to the set point, set point entirely depends upon what is the gain that we have set. And because of higher gains, there are also chances of generating overshoot. Here we can see, because of the higher gain, it is pumping higher amount of current, there is a little bit of overshoot. If that overshoot is okay, that's fine. If not, we have to go with a smaller gains, or we have to go with a different differentiator, right? Also settling time. Now if you see 48.9, this is 50. So we have to wait for some more time to settle it down. So almost it is taking somewhere around, right now it is at 3 seconds. So right now it is at 50.3. So almost settled. So by using a P controller, so when it cools down again, it is pumped with a little higher current, again started heating it. So it's still not yet settled, it's keep on fluctuating, right? That's a problem with your P controller too. So one way to realize is by using a Ki gain too. So let me stop at this point, and I'll decrease the Kp gain and slightly increase the Ki gain, so that we can understand by using I gain, adding an I gain, how fast it can reach to the set point as well as it reaches to the settling point too. Right. So let it cool down. So just to cool down, I am unplugging the power supply unit. So it will cool down. So right now the temperature has reached to 30 degree. So I have set a gains Kp gain as 0.02 and Ka gain as 0.062. Now we can see what is the time it takes to reach to the set point. Let me run, and I am applying the power. So you can observe started heating, and with no time, almost with 3 seconds, 4, set 43, and it reached to the set point 47 somewhere and reached to 49, 50.8. Now it will try to maintain. So that is an advantage when compared with P controller. The PI controller, it can have fast response as well as it can reach to the steady state error very fast. So that entirely depends upon the what is the gains that we have set for Ki as well as Kp. Still it is in fluctuations, not at reached to setting point. Settling point can be calculated 1 or 2%, 5% of your set point. So now it is almost at 49.4 degree, almost settled. So that is the difference between a normal on-off controller and your proportional and integral controllers. So in case of on-off controller, it will be on-off, something like that. But whereas in case of P or PI controller, it will control, right? It will try to control to the set point. .6. If this plus or minus 1.5 degree is okay, we can go with these gains. If not, we have to slightly increase the gains of I controller or P controller. So let me change it to somewhere around 0.08. So it is completely a manual tuning. So this is how to do the manual tuning. We can see at this particular point it started almost close to that of our set point, right. So this is a way we can understand how can we make use of a data acquisition unit as well as software in loop system. And so and working with real world signals as well as the software, interfacing both together. So system or using a data acquisition to the real world hardware system, and controlling the temperature of a plant. So this is how this is a simple case study to make you understand about the working of a data acquisition as well as working of a controller using LabVIEW as well as a closed loop control system, as a software in loop system. Thank you.